Hello and welcome to York Universe, the astronomy and astrophysics radio podcast, written and presented by the students, faculty, alumni, and friends of York University. You'll find us now wherever podcasts are distributed. I'm Sana, I'll be one of your hosts this evening, and I'm joined today by Paul Mackin. We're broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time or Tuesday, 1 a.m. Universal time on YouTube at York U Observatory in concert with our online public viewing program run by our observatory team. To navigate to the live show or to find out more, please check out our website at yorku.ca/science/observatory and follow the links to our online public viewing on our YouTube channel. For any questions or comments you have of our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on our Instagram with the handle at YorkU Observatory and on Facebook at Allan I. Carswell Obs. And finally, all of our programs are free, but if you would like to make a donation, please see our website at yorku.ca/science/observatory. Our crew will be monitoring the YouTube chat room for questions and posting content. The current weather is actually looking pretty good. We're finally, breaking our bad luck with the weather and starting to get some nice clear skies. So in a few minutes, we'll actually be bringing you some live views from the Observatory 1-meter telescope. That is, of course, unless the weather changes in the next 15 minutes or so, but let's hope it doesn't. But Paul, how are you doing tonight?
I'm doing great. Thank you for asking. Yeah, it's nice to see the weather starting to get a bit better. I was noticing tonight that the skies are clear, and I may actually take my own scope out after the broadcast tonight. So it's always makes me feel good when we get to start observing on a more regular basis.
Yeah, it was really depressing this past winter, honestly. I know I was really wanting to do some observing over the winter break when people are actually like available to come observing, but it was just, it really felt like a solid 2 months of just like clouds and snow and cannot observe in this weather type of thing. So it's definitely nice to see that starting to break up a bit.
Yeah, it was almost tragic because every week we were hosting the show, it was always cloudy, no live
Yeah.
observing. So tonight we'll
Yeah.
get some live observing. That's great.
Yeah, finally. We definitely did have some good luck last week on Thursday night with the lunar eclipse. We didn't run like an official observatory event, but a couple of us just went up to the rooftop of the Arboretum parking garage with the 40 centimeter telescopes and a couple other telescopes to watch the eclipse. CTV News actually paid us to visit and got some footage of the eclipse with us. So it was a lot of fun. But Paul, did you manage to see the eclipse at all?
Unfortunately, no, I was traveling and I
Mm.
missed it. And when I eventually did get home, I was so exhausted that bed was the only place that I had in mind. But interestingly, where I was the few days before that, I managed to get a couple of nights. I actually took a telescope with me, and a couple of nights I got some great pictures of the moon leading up to
Ooh.
it. But then my travel plans got kind of messy, and I missed it. So the good
Mm.
news about lunar eclipses, though, they are more common than solar eclipses, and it's I'm sure there'll be another one before too very long.
Yeah, I think about sometime next year, there's going to be at least a partial lunar eclipse.
I believe that to be the case. Yeah, and
So,
there was a
yeah.
partial last year as well. Yeah.
Yeah, it was really cool this time though, because we really got like the entire lunar eclipse here, a full 6 hours from start to finish. We got it all here. So we actually just kind of sat and watched the moon as the partial started and then the total and this really beautiful like blood red moon over Toronto. I gotta say it does look a little bit weird having the moon look so red during the eclipse just because it's so faint. Like I'm so used to the moon just being this bright thing in the middle of the sky, but it was quite odd seeing it just hanging overhead being very faint, but it was a really beautiful eclipse.
Yeah, I've seen them as well, and you've described it perfectly. That blood red color, and it's dim, and it's just kind of
Hmm.
eerie, but also
Yeah.
very exciting.
Yeah, it was really cool. And I'm actually glad that we did get so much of the totality. So we did see the whole thing. It wasn't just a little bit of it. This is not the first time I've seen a blood red eclipse, but it was the first time that I watched pretty much the full thing from start to finish. But did start to get a little bit tired around 4:30, so we kind of packed up early. But it was a great experience.
Well, I saw a lot of the pictures the team has gathered, and they were great. But I will note that some of my classmates are still recovering from the lost night's sleep. So,
Yeah, I had a very good sleep when I got home. Kind of turned nocturnal for a little bit there because I just slept the entire day. Um, but yeah, it was definitely worth it for a lunar eclipse.
well,
But
we will only undergrads, unfortunately, had class the next morning. So,
yeah, I had a meeting on Friday morning that thankfully got canceled at the last minute, so I didn't have to make an excuse about why I wasn't there. But just kind of worked out well. Yeah. But we have a great show tonight, lots of interesting history and news items to talk about. So I think we should probably just hop right into that. I'm up first tonight for This Week in History with March 19th, 2008, when a very, very bright, even naked eye gamma ray burst went off in the night sky. So just taking a step back and talk a little bit about gamma ray bursts, or GRBs for short. These are relatively rare, very, very intense bursts of radiation. They usually are a result of things like supernova explosions, when the most massive stars in our universe die and transition into either neutron stars or black holes. So these are some of the most energetic events in the history of in really our universe in general. So, of course, they produce very, very energetic events. Gamma ray bursts, in particular, what happens with these is that the explosion triggers triggers two jets that are coming off of the remnant that's left behind after the explosion, just sort of 180 degrees apart. They kind of shoot off in two different directions. And in these jets, it's just really full of a whole bunch of light and a whole bunch of radiation. The light that comes off of these things is really at all wavelengths, so you can observe it in visible wavelengths and radio and infrared. But because the bursts of energy are so energetic and so really crazy, a lot of the radiation that comes off of these events are gamma rays. Hence the name a gamma ray burst, because you'll just see this like burst or this flash of gamma rays that comes off of this event. The initial burst can last anywhere from milliseconds to hours, but after that, there's a much longer kind of cool down period where there's an afterglow that comes off of the GRB that can continue to be bright for, I think, something of up to weeks, potentially even months, depending on what happens. So what happened on March 19th, 2008, is that the Swift Observatory, which is a gamma ray observatory, I believe operated by NASA, at 2:12 a.m. EDT, detected a GRB that was called GRB 080319b. I am not familiar with what the numbers stand for. It could just be coordinates or a time. I'm not really sure. But it turns out that this gamma ray burst in particular originated from a galaxy about 7.5 billion years in the past. So this event itself happened before the Earth had even been born and was only reaching the Earth 7.5 billion years after it had happened. Now, GRBs themselves are somewhat common. The Swift observatories, like the Swift Observatory, will usually pick up a couple of them a week. So they're not exactly the most common thing in the universe, but they're also not the rarest thing. But the thing that's particularly interesting about the one that happened on March 19th, 2008, is that it's the most intrinsically bright object ever observed by humans in the universe. So that was a quote that came from, I believe NASA, but I'm not entirely sure where that quote came from. And that was just because this thing was just so crazy bright, you could see it with the naked eye. And because it's so far away from us, it was the most distant objects that humans have ever been able to see with the naked eye. So a very, very remarkable event. A little bit more detail about what the actual event itself is. The burst lasted for around 50 seconds, reaching a peak magnitude of 5.7, and then remained brighter than around ninth magnitude for 60 seconds. The afterglow from this event was also visible to the naked eye for around an additional 30 seconds. So overall, a pretty long period of time that this really just bright object showed up in the night sky that could actually be observed by the naked eye. So it's definitely a very significant event. Would have been awesome to see it, although I don't think I would have known what it was if I had actually been observing the night sky at that time. And just for reference, just another point of reference for how bright this GRB was, it's around 2.5 million times brighter than the brightest supernova explosion had ever been. And if you were to put this in the center of our solar system where the sun is, it would look to us on Earth, it would have an apparent magnitude of minus 67.57, which is 21 quadrillion times brighter than the sun. So absolutely wicked object, significant just on its own for how ridiculously bright it was. But in terms of some research that came out of this, it helped us kind of understand how we see gamma ray bursts and how we observe them and kind of what their origins are. And it really just highlighted the importance of not only the initial burst of energy, but the orientation of those jets that come off of the gamma ray burst. Because it turns out the reason that we see some gamma ray bursts is just because their jets are pointed at us. So gamma ray bursts themselves are technically a lot more common than what we actually observe. But what happens in most cases is that the jets coming off of the gamma ray burst just aren't pointed at us. So we never see them. And what happened with this particular gamma ray burst on March 19th, 2008, is that the jet was just pointed straight head on right at us, which is why it looked so insanely bright. And in some other cases where we do see these GRBs, the jets are not so well aligned with the Earth. They're kind of a little bit off center. So while we do see the burst of gamma rays, we just don't see it as bright as it did in this case. So definitely a very interesting event. Again, would have been amazing to see it. But I guess we're just going to have to keep stargazing and hoping that another gamma ray burst goes off in the night sky.
Yeah, and I noticed, the it being named the Clark event after Arthur Clark, just a few hours
Mm-hmm.
after his death. That would have been, he would have liked that very much, I think.
Mm-hmm.
He was a visionary, and he was a keen amateur astronomer. So that's just sort of a nice little piece on the story as well.
Yeah. Yeah, astronomers give such silly and ridiculous names to some things that it's kind of nice when they pick a very fitting name for something, kind of like in this case. Yeah.
So I guess also this week, March 16th in 1750, Carolyn Herschel, who was the sister of William Herschel, and we've talked about him many times. He discovered the planet Uranus, among other things. And she was an astronomer of considerable accomplishment in her own right, although a bit reluctant to join the field, as she actually wanted to be a professional singer. She helped her brother and eventually developed a keen interest uh, in the field and skills to match. And this was often sadly the case, her brother really kind of just attempted to use her as an unpaid assistant. But in her own right, she discovered several nebula and 8 comets. And she published a stellar catalog with, I love this name, charming name for the catalog, Catalog of Stars, taken from Mr. Flamsteed's observations contained in the second volume of Historia Coelestis, I think I got that word right, and not included in the British catalog. Unfortunately, when it was published under her brother's name, but it was her work, and the catalog was reworked and expanded, and eventually given the name the New General Catalog. And it is still in use today. You'll hear NGC 1740, which is a galaxy. Then it's always referring to NGC. That is one of the standard catalogs astronomers use to list objects. And in 1928, the Royal Astronomical Society presented her with their gold medal for a lifetime of work, which was not given to another woman, believe it or not, until 1996, when it was awarded to Vera Rubin, who we've also mentioned on this podcast many times. She of the Vera Rubin Observatory fame. That observatory is coming online this year. So Carolyn spent her last years assisting and mentoring her nephew who was William Herschel's son, Sir John Herschel. And he was a polymath, an English polymath, active as a mathematician, astronomer, chemist, and inventor. She died in 1847 at 97 years old and left the world a better place because of her considerable volume and quality of work.
So the NGC catalog originated with Caroline Herschel then.
Yeah, it did. That's where it became
Wow.
yeah. I mean, it went through several iterations, but the catalog of stars taken from Mr. Flamsteed's observations contained in the second volume of Historia Cholesticis and not inserted in the British catalog morphed over a period of years into NGC.
Hmm. That's really interesting. I read about the NGC catalog a few times and I had never realized that. But it's such a widely used catalog. You think that's something that might might show up a bit more obviously in information pages about it.
Yeah, and you got to admit, NGC is an easier name.
Oh yeah. Yeah. Um
But I mean, in a way, her story sort of foreshadowed what's happened to a lot of women in science, and hopefully, and I would say I would be optimistic about this. That situation has improved a great deal, but
mhm,
I mean, most of the work had to be published in her brother's name. She was recognized I think, after his death for it,
mhm,
but sort of quietly. And then, I think of the number of uh, contributions that women have made to astronomy between 1828 and 1996. And I'm sure there's some gold medal work in there somewhere from women.
mhm.
Like unfortunately, it represents just a bias that hopefully we're seeing less of.
Yeah, yeah, I can definitely think of a couple notable examples where that happens, but uh it definitely has improved since the sort of time frame we've been talking about here. Uh, but yeah, it's definitely sad to see that happen. At least some women were given the recognition some years later, but
And I don't know
yeah,
if she was a good singer or not, but she was a hell of an astronomer.
yeah, yeah. But we also have another interesting history item on March 17th, 1852. So still around this pretty similar time frame, a very, very long time ago, which was the discovery of the asteroid 16 Psyche. Now, 16 Psyche is this what's described as a potato-shaped asteroid that orbits the sun in the asteroid belt. So this is considered, not considered, but it is just kind of a big cloud of asteroids that is in between the orbits of Mars and Jupiter. 16 Psyche itself orbits at a distance of around 2.5 to 3.3 astronomical units away from the sun. So around 2.5 to 3.3 times the distance between the Earth and the sun in the asteroid belt. Now, one of the reasons that 16 Psyche is a very interesting asteroid, and one of the reasons that we're talking about it today, is partly because of its composition. Now, the composition of most asteroids is primarily things like sort of ice. There are a lot of asteroids that have elements like, or heavier elements like rocks or metals like iron or nickel. But 16 Psyche itself is kind of unique in this respect because it just has a ridiculous amount of rock and iron and nickel and other sorts of metals. The metals in particular, it's now estimated make up around 30 to 60% of the mass of 16 Psyche, which is significantly more than any other asteroids that have been discovered in our solar system. So the exact composition of the asteroid is kind of under debate, and the percentages of how much mass is being taken up by metals has sort of varied a lot. There's obviously pretty huge error bars on a 30 to 60% mass estimate for 16 Psyche. But regardless of the details here, it is really a very unique type of asteroid just because it has so much metal in it. So it's a very interesting object even today that has warranted quite a bit of study. But going back to the actual discovery of the asteroid in 1852, it was discovered on March 17th, 1852, by the Italian astronomer. I am probably going to butcher this, so if you know how to pronounce this better than I do, please correct me. Uh, Annibale di Gisparis, who ended up naming Psyche after a Greek goddess. So the name Psyche itself was, I guess, just the name that had been assigned to the asteroid. And then the number 16 indicates that this was the 16th minor planet that has ever been discovered in our solar system. So, like I said a little bit before, 16 Psyche, even today, is still a very, very interesting target. It's been studied by several different kinds of telescopes, which have sort of helped to understand its composition, understand that it has this kind of potato-ish shape to it, and it doesn't really look spherical like some other asteroids. But it also appears to have a couple of big impact craters on the surface. Now, on top of all of the sort of investigations and observations into 16 Psyche that have already taken place, NASA has also launched a whole mission to asteroid 16 Psyche. Just going back to the whole astronomers are terrible with names things. NASA decided to just name this mission the Psyche mission. They're not giving it a different name like they might have for different missions. So the Psyche mission to asteroid 16 Psyche. Particularly what the Psyche mission is going to do is it really wants to try to understand more about the formation of the asteroid 16 Psyche. So it's going to be doing things like mapping the surface, getting a better understanding of the composition, just to understand how it formed over time. And the reason that its formation is a really interesting topic and something that NASA will spend a whole bunch of money to launch a mission for is just that because there's so many heavy metals in this asteroid, it's kind of suspected that this was actually a failed planet. So it's a planetetesimal, essentially, where it's like the core of a planet like the Earth, or maybe a bit smaller, that eventually had the outer layers of the planet stripped away as a result of a whole bunch of collisions over millions or billions of years. Massive collisions like this were actually very common in the early history of the solar system. Our moon, for example, seems to exist only because there is a massive Mars-sized object that collided with the Earth and then ended up spewing a whole bunch of material off of the Earth, which eventually ended up coalescing into the moon that orbits us now. So these sorts of collisions were incredibly common, and it seems that 16 Psyche was formed out of those types of collisions. So understanding its history and its formation can really help us to better understand the history of our solar system and also the history of the Earth. So it's a very, very interesting object to study even today. Hundreds of years later, again, it was discovered in 1852. We're now 2025, and it's still an interesting target. So the Psyche mission in particular launched towards 16 Psyche on October 13th, 2023. It's on the way there now. It seems to have been snapping a couple of pictures of our solar system along the way. And it's suspected that it's going to reach 16 Psyche in July 2029, where it's going to be put into orbit around 16 Psyche and begin its science mission. So definitely something to keep an eye out for in July of 2029, and what interesting things the Psyche mission will discover about 16 Psyche.
Yeah, I was just looking at the NASA website for it, and right now it's in a cruise mode,
Mm-hmm.
uh, and it's going to fly by Mars in about 14 months. And then after
Oh,
that, yeah, it's going to do a flyby of Mars, and there will be some science gathering there, May 2026. And after that, right now it's just sort of using gravity to get to where it needs to be. It's basically it's in an orbit that'll take it out to Mars, and it'll pick up some energy at Mars. And then it's got a really unusual engine design. It's an ion engine, which doesn't put out a lot of thrust, but you can fire that ion engine for you know days, weeks, months, even years, and it just uses a little bit of fuel, which is a gas which is converted to a plasma by electrical energy from the solar panels on the spacecraft, and so it puts out a very small amount of thrust, but it's continuous, so it keeps building up. You get this very small but constant acceleration, which really can change the orbit of the spacecraft with very little fuel expenditure. So it's using that to adjust its orbit out to Psyche, and it'll match orbit with Psyche and go into orbit. It's going to be I'm very excited about this mission. There's also, because Psyche is thought to be a metal asteroid or largely metal, there are also commercial interests because maybe that's a place you could mine eventually, but that's sometime down the future.
Yeah, just I'm very much looking forward to this as well. It's going to be definitely an interesting mission. But we have we should probably move on to the next this week in history item, which is back to you, Paul.
Yeah, so I'm going to take us back to March 5th, so not quite this week, last week kind of thing, 1979. That on September 5th, 1977, the Voyager 1 spacecraft, which was launched on March 5th, 1979, sorry, it was launched on 1977, and on March 5th, 1979, it completed its first flyby of Jupiter. And that was over 46 years ago. It wasn't the first explorer of Jupiter. That honor goes to pioneers 10 and 11, which were 6 and 5 years earlier. The Voyager 1 and its companion spacecraft, Voyager 2, are unique. After visiting Jupiter, it went on to explore Saturn and then fly by Saturn's moons Titan before heading out of the solar system. It was the first spacecraft to cross into interstellar space, which it did in 2013, 36 years after launch. In 1990, the last act of its cameras before they were deactivated was to look back at the solar system from 6 billion, that's with a B, kilometers out and take a family portrait of the planets. While it couldn't get Mercury and Mars, they were both too small, it did produce a striking image of the sun along with Venus, Jupiter, Earth, Saturn, Uranus, and Neptune, and each are only a few pixels wide. And if you want to see this, you can just go on Google and look up, Voyager family portrait. That's what it's called. The image of Earth is inspiring. It's tiny but distinctly blue, and it was captured as if appearing in a sunbeam. I remember when this image was published, Carl Sagan, who pushed for this last bit of Voyager imaging, described it as a pale blue dot and commented that everyone who lived was captured in this image. Every human that lived or ever lived was in one way, shape, or form in this image. He later wrote a book called A Pale Blue Dot, A Vision for Human Future in Space. It was the second last book before his death. And he used this image to lay out both a philosophy and a plan for human space activity. Voyager 1 and its sister spacecraft Voyager 2 continue to this day, operating nearly 48 years after launch. And yes, they're becoming increasingly creaky with old age, and there's been some outages, and they've had to turn off, systems and turn on backup systems and shut down science instruments. But the spacecraft has enough power for a slimmed down extended science mission in interstellar space for another 10 or 11 years. But take a moment to think about that phrase and what it implies. Interstellar space. Humanity, something we built, is on its way ever so slowly to the stars.
Yeah, I gotta say that the Voyager missions are some of the, in my opinion, like the best missions that humanity has ever launched. I mean, I love some of the more recent missions, like big fan of missions like JWST, but the fact that the Voyager space probes so many years later are still working and, like you said, are venturing out into interstellar space is just so insane and so remarkable that these have to be some of the most interesting missions that humanity has ever launched. I'm not sure if you agree with that, but they definitely are some of my favorites.
They're fantastic. If you think about it, they were originally launched with the intention of visiting Jupiter and Saturn, but they got to Jupiter and Saturn both, and then one went on to basically become our first interstellar probe. The other one became our second interstellar probe after also going to Uranus and Neptune. And the only images we've had from Uranus and Neptune are from Voyager 2. And a follow-up mission is in the early planning stages for Uranus, Uranus orbiter, but it's going to be 2030s, 2040 before it gets there. And so they've given us all the data we've got of the outer planets. Further, the amount of information, we've now got a good feel from Voyager 1 and Voyager 2 of what the shape of the solar wind is, the heliosphere, the heliopause, and what the boundaries are for interstellar space, which gives us a huge knowledge base to operate from in determining models for how the sun works, how it interacts with the rest of the stars in the galaxy, and as the galaxy rotates and so on. So they've really moved our knowledge, not just of our solar system, but of interstellar space to levels that we couldn't even imagine before they were launched.
Yeah.
And they're still going. This mission, it could make 60 years. It could still be operating. It'll be very close to dead 60 years after launch. And that is remarkable.
Mhm. It's also just really interesting to think about how so many of these missions that get launched end up being used for things that weren't really in mind. Nobody really had in mind at first. So when you launch something, you might have a certain lifetime in mind, but if things go well, you end up in a position like we are right now, where it's just doing so much more science that it had ever intended to do at first. So just yet another one of the reasons why the Voyager missions are so amazing. But that brings us to around 30 minutes into our show, so should probably go to our reminders. But for anyone who's just tuning in, you're listening to York Universe, broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. Please visit our website, yorku.ca/science/observatory, to navigate over to our online public viewing chat room and for any questions you might have. Tonight, you're listening to myself, Sana Withers, and Paul Mackin discussing some astronomy history, and we've got some new news items coming up as well. But we do have a couple of reminders for you before we get there. To start off, please keep in mind we are still running tours on Wednesday evenings. So if you would like to attend the tour coming up this Wednesday or the week after, please visit our website, yorku.ca/science/observatory, and grab some free tickets to the events. The event is free, as with all of our, or most of our tours, but we just need people to get tickets ahead of time so we don't get bombarded with people. There's limited space up in the observatory, so we can't just let everybody up at the same time. But the forecast for this Wednesday is actually looking kind of decent, so we might be able to do some live viewing on the Wednesday tours. Also, a reminder for anybody thinking of going to the Astronomer in Residence program at Killarney Provincial Park. The applications are open for air this summer, and they do close earlier than last year, so they're closing in May this time around. So if anybody is thinking of attending those, please go to our website. We have a dedicated area for the Astronomer in Residence program, and you can submit your applications there. I also want to point out that if anybody is in our online public viewing chat room, we are looking at Mars. So it is actually clear out finally at York, and our wonderful observatory team is bringing us some live views. They were on the Orion Nebula earlier, and then Capella, and right now we're checking out beautiful Mars. But Paul, you also have a reminder for us? Paul, are you there? Oh, I don't see him. Maybe he was having some internet troubles, but so we'll come back to Paul's reminder in just a minute. Oh, his internet died. Well, he will be reconnecting in a moment, so we'll let him do his reminder when he gets back. But in the meantime, let's just move on to discussing some news in astronomy. Now, there's a couple of interesting things that have been happening in astronomy over the past few weeks, but one thing that I have been very, very excited about since Tuesday last week is that we now know what JWST is going to be observing in what's called cycle 4. So if anybody's ever wondered how JWST decides what to observe, basically what happens is that once a year, the people who manage the James Webb Space Telescope at Space Telescope Science Institute will put out a call for proposals where anybody who wants to use the telescope for any of their science can submit a proposal that outlines what they want to do with the telescope and why it's important science. Then all of that gets reviewed by a committee. The proposals get ranked, and the ones with the highest ranking are the ones that actually end up getting time on the James Webb Space Telescope. So what's called Cycle 4, which is JWST's fourth year of science, the proposals for that season of observing were submitted in October of last year, and we just got the results after a months-long wait last week. So we now know what JWST is going to be doing in the 2025-2026 season of observing. Now, there's a whole bunch of really interesting stuff that is sort of distributed over 274 different programs, totaling 8,500 hours of science in Cycle 4. So just a quick summary of some of the really interesting things that JWST is going to be doing over the next kind of year and a half. So to start off with extragalactic astronomy, so studying galaxies and even our galaxy itself, there's going to be tons of spectroscopy. The first 3 years or so of science on JWST have given us a whole lot of really interesting galaxy candidates. So these are objects that have been detected in galaxy imaging data that just look very interesting. There's a whole lot of galaxies in this data that are what we call high redshift galaxies. So these are galaxies that exist within the first billion or so years from the Big Bang. These are very interesting objects because they're just the first generation of galaxies to form and evolve in our universe. So by studying them, we can learn a whole lot of things about the way that galaxies formed and evolved and galaxy evolution, and even the impact of things like dark matter the impact that things like dark matter have on the formation and evolution of these galaxies. So there's going to be a whole whack of time in Cycle 4 dedicated to just trying to get a deeper understanding of these objects. This is going to happen through spectroscopy, particularly with the near-infrared spectrograph, that's going to be taking these high-resolution observations of these galaxies to kind of understand what they're made out of and the dynamics that are happening within these galaxies. So, like I mentioned, a lot of these are happening within the first billion or so years since the Big Bang. There's quite a bit of science that can be done with those galaxies. But one of the, I guess, highlights of this next Cycle 4 is particularly going to be looking at the earliest, very first galaxies that came into existence within our universe. These are objects that are found within the first 300 million or so years since the Big Bang. It's what astronomers call cosmic dawn. It's exactly what it sounds like, just really the first generation of galaxies to come into existence in our universe. Not only are the astronomers going to be studying this using the near-infrared spectrograph, or NIRSpec, it's going to be using a different instrument also, which looks at more the mid-infrared part of JWST, so longer wavelengths than a lot of the other instruments, where it can really help us understand or get a better understanding of the dynamics and the compositions of these galaxies compared to just NIRSpec itself. So there's going to be just a whole bunch of different spectroscopy being done on those, which is very awesome. On top of that, there's going to be a couple of programs that focus more on imaging instead of just spectroscopy. Now, the imaging, and the reason why this is also a very important thing to keep doing, is that when you keep imaging different areas of the sky, you're going to keep coming up with more galaxy candidates. So there's two imaging programs that I need to call out here because I'm very, very excited about these. And they're both centered in Toronto. So there's one program that's come out of York University by Professor Adam Muzzin called Minerva, unlocking the hidden gems of the distant universe and complementing HST and JWST's imaging legacy with medium bands. That's definitely a bit of a mouthful for a program title. But what Minerva is going to be doing is it's going to be following up existing fields that already have imaging and data from the James Webb Space Telescope and the Hubble Space Telescope, but using different sorts of imaging. So instead of the typical imaging that a lot of these telescopes have already given us of these fields, he's particularly going to be following up these fields with what's called the medium bands. These bands just have a higher spectral resolution than the existing observations on those fields. So you'll be able to get much more detailed information about those galaxies than what's currently available. So even though we're still imaging fields that already have lots of data on them, you're going to be able to find out a lot more information about the galaxies in there. So it can, in some cases, help to improve, measuring things like the galaxy properties by a factor of 4. So there's going to be a whole bunch of science that comes out of this program. And one of the really awesome things I got to mention about Minerva is that it is among the largest JWST programs ever. So we can sort of quantify the size of a program by the number of hours that were assigned to it, where larger programs, as you start to add more and more hours, they just become even more rare. It's just hard to give a lot of programs a whole lot of hours on JWST because it just kind of eats up the amount of time that's available. So in this cycle, in cycle 4, there have only been 8 programs assigned that have time allocations more than 130 hours. And Minerva has a total of 260 hours. So this is among the largest JWST programs that have ever been completed since day one in the past 3 to 4 years. It's also the largest program that has been assigned, that has been awarded time in cycle 4. So this is super, super exciting. Very excited to start working with this data set and to see what it has to show us about the universe. And on another note on Toronto astronomy, an astronomer at the University of Toronto, Seiji Fujimoto, was awarded 250 hours that's going to be spread out over a couple of different years for a program called Venus. Now, despite the name, this doesn't have anything to do with the planet Venus. Venus is just an acronym for the Vast Exploration for Nascent Unexplored Sources. This is going to be a program that will image 45 different galaxy clusters in order to search for the faintest galaxies in our universe and some of the most distant ones. So together with Venus and Minerva, there's going to be a whole lot of very interesting science that comes out of these. Hopefully, we're going to detect a whole bunch of different galaxies and galaxy types that have never been observed before. So very interesting science, and just definitely had to highlight them on York Universe since they are both programs coming out of Toronto, particularly Minerva coming out of York University. Now, on top of just looking at galaxies and extragalactic sources, there's also quite a bit of time on JWST that's devoted to studying planets and exoplanets. Now, exoplanets themselves are just stars that or planets that orbit stars that are not the sun. This, I think, is a relatively new or relatively younger field of research in astronomy as opposed to just sort of planetary science or other fields. But now we're kind of at a point where there's a whole bunch of known exoplanets. These are the results of other telescopes like the Kepler Observatory, for example, who really dedicated and spent a lot of time trying to detect exoplanets and planets that orbit other stars. So there's now a whole bunch of potential targets for JWST to start following up on and really trying to characterize and understand these systems of exoplanets and the stars that they're in orbit around. And speaking of planets, we're also on the planet Jupiter on the 1 meter telescope right now. There's Jupiter in the center, and you could see 3 of its moons sort of kind of look like they're trailing along the planet right now. But getting back to the exoplanets on JWST, there's multiple programs that are going to be studying the atmospheres of rocky planets, including some super Earths that are actually relatively close by to us. So these are definitely interesting objects, especially when you're looking for potentially finding habitable exoplanets. So among studying the atmospheres, they're going to be looking for certain biosignatures, so certain compounds and elements that are potentially required for life or a byproduct of life. Detecting these biosignatures is not necessarily 100% for certain saying that we have identified life in the universe. It's not necessarily what detecting these biosignatures means, but they're definitely a very interesting thing to search for and trying to understand the atmospheres of different exoplanets and assessing if they're habitable or not. There's also going to be a lot of time dedicated to looking at exoplanets that are orbiting what are called M dwarf stars. These are the lowest mass stars that exist in our universe, and they're also incredibly common. They make up around 75% of the stars in the Milky Way galaxy. So if you're looking for habitable exoplanets, M dwarfs are a very good place to look just because they're so common. The problem with M dwarf stars is that they're also quite unstable, much like how our sun is flinging stuff off of its surface at us that cause these beautiful aurora. M dwarfs are actually very, very good at this. They can emit a lot of very high energy flares off of the surface of these stars that can then actually potentially cause problems for any life that might be evolving on the surface of planets in orbit around them. So there's also going to be quite a bit of time on JWST dedicated to looking at the sort of dynamics of M dwarfs and how those flares can influence the planets or the exoplanets themselves. Now, on top of that, one other thing I should mention is that there's going to be multiple follow-up observations of targets like Jupiter and Saturn. Jupiter, there's going to be a bunch of observations looking into the atmosphere and the banding and the storms on Jupiter to understand more about its atmosphere. There's going to be programs that investigate Saturn's ring system and also the magnetic fields and environments of the ice giants Uranus and Neptune. So a whole bunch of really interesting stuff that's coming, that's going to be covering a whole bunch of different areas in astronomy out of JWST. And the super exciting news that we have 260 hours of time on the James Webb Space Telescope right here at York University. Even on top of that, another professor at York University, Charles Edouard Bouckaret, is a collaborator on a program that's going to be investigating lava planets with JWST. So he and his team got 100 hours of time on JWST. So yeah, lots of great stuff happening with James Webb at York University and University of Toronto. But Paul, I see that you're back.
I am back. Yeah, I was talking away and my internet went away. I guess the foibles of modern technology. But
Yeah,
no, this is
it
very
took
exciting. I was listening to you, and you and I were talking about it beforehand. And I guess one question for you: are you going to be involved in any of that 260 hours?
yes, I'm a co-investigator on the program,
Outstanding! Congrats.
which is insane.
At this point, I sort of bow down and go, "So not worthy, so not worthy." But that's very
It
exciting.
it still feels kind of insane. Like I remember we found out the results on Tuesday around 10 a.m. on Tuesday, and I don't think I did much of anything on Tuesday. I was just so excited about it. But it's really great news. I'm so happy about it, and really
Well,
looking forward to starting to get this data to start rolling in.
no, it's very exciting. And it's interesting. I mean, you think about it, that's a significant amount of time. That's more than 10 days of total observing time. And if you th
Yes.
and given that JWST has a 10-year lifespan and is not particularly serviceable, that's a significant percentage of the total days of observation time available.
Hmm.
Very well done. I mean, that's so exciting.
Yeah, it was really Adam's program, and there were two co-primary investigators, which were other collaborators of his. So it was really their baby, their child, that got time on JWST. I did help with some of the science and a couple of the figures, but it's so exciting that we were actually able to get that observing time.
Well, I
Um,
mean, it's wonderful that Canada is such a player in this space. I mean, we
mhm.
contribute to these programs, and we're involved, and we publish
Yes.
really good science. We publish really good science.
Yeah. University of Montreal also got several programs on JWST this time around. But for anyone who knows the different universities and their little niches, University of Montreal is primarily an exoplanet sort of university. So they've got tons of time for exoplanet science and planetary science at U Montreal. And York U and U of T got a lot of extragalactic time. But um, speaking of time, we are kind of running short on
Yes,
it.
we
So
are. And
to
and and,
avoid,
and
oh,
speaking of Canadian science, A couple of weeks ago, we were discussing on our 600th episode Saturn, and one of the hosts mentioned the enormous number of moons that Saturn has. And at the time, there were 146 moons. Well, just last week, a Canadian Taiwanese team using the Canada, France, Hawaii telescope discovered, get this, 128 new moons, taking the total up to 274. And between 2019 and 2021, the same team discovered 62 moons. So they now have 190 Saturnian satellite discoveries under their belt. Now, these moons are all in the range of a couple of kilometers in size and are probably fragments of captured objects that may have had impacts within the Saturnian system itself. But this is incredible because when I was a kid, I'm a bit older, but when I was a kid, Saturn was thought to have the second largest number of moons of any planet in the solar system. Jupiter supposedly had 12, and Saturn had 9. Well, 5 decades of exploration by telescopes and spacecraft have greatly changed that picture. Jupiter is now confirmed to have at least 95, and Saturn appears to be winning this contest with nearly 3 times as many. But, this is kind of typical in astronomy. Some things are thought to be one-ofs or somehow special and unique, and then we look closer and discover that a lot of our assumptions are oversimplified. An example of this, Pluto didn't have a moon, then it had one. And then we got close up to look at it with the New Horizons spacecraft, it had 5. Another example, Saturn was the only planet in the solar system with rings. Then Uranus had them, then Jupiter, and finally Neptune. So all of the gas giants in the solar system have rings of some sort. There's so much to discover in our solar system when we've just started. When I think about this, I'm often reminded of the famous quote from Hamlet: "There are more things in heaven and earth, Horatio, than are dreamt up in your philosophy." And of course, that line was written around the time that we started this journey.
Yeah, it's really remarkable. I was just talking about galaxies and exoplanets, and even here we are sitting in our own solar system, so close to some of these things, and we're still discovering new things about them. So there's really, I guess, no limit to how complex a lot of these systems can get and the amazing things we can discover about them.
And
But
there's
yeah,
also this, yeah, there's also this whole idea of a Copernican view, like we thought that we were the center of the universe and the center of the solar system, and then Copernicus showed us, well, that wasn't quite right. But every time we look, we're less and less unique, but we're part of such a beautiful tapestry of a universe with incredible structures and such a great science story to tell. It's overwhelming, but it's also, I think, just joyous.
hmm yeah, it still kind of boggles my mind that Saturn has more moons than Jupiter, because I've always thought, like you said, of Jupiter being the one that has the most moons. That's always kind of made sense to me, just because Jupiter is larger than Saturn. It's also closer to the asteroid belt, so there's lots of stuff for it to kind of pick up, lots of these small moons for it to pick up. But it's really insane, 274 moons of Saturn.
And of course, you're going to have to get into how we define moons as well, because, Jupiter, these are not moons per se, but Jupiter has Trojan asteroids. A lot of asteroids before it in its orbit and after it in its orbit. Saturn probably does too. How do you define those? The picture is increasingly complex. We've actually got a
Yeah.
spacecraft on the way to look at those Trojan asteroids. So, we're going to learn a lot.
So what you're saying is we're heading towards round 2 of the Pluto debate, where the IAU is going to have to step in and enforce a new definition of what constitutes a moon versus,
Yeah.
I don't know, a minor moon, maybe?
Yeah, I don't know because, like some of these moons are really, really small. Is Titan the same as, a 2 kilometer chunk of rock broken by a comet off a slightly bigger chunk of rock.
Hmm.
So there is going to be that kind of debate. There's going to be that reclassification, but that happens all the time in science as we learn
Hmm.
more, you know, and as our understanding of scale changes and so on. So this is a healthy thing.
Hmm. But we did miss this earlier, actually, Paul. You have a reminder for us.
Right. Yes, I do. So today, one of my classmates, who's actually on the OPV right now, pointed out to me because I mentioned that I'd missed the eclipse to him, the lunar eclipse, that there is a solar eclipse at the end of this month. And it's a partial eclipse, but it's a relatively big partial eclipse, upwards of 90%. Unfortunately, that's somewhere, kind of over the North Atlantic near the Arctic Ocean. Um, on, for us in Ontario, I think if you're in Eastern Ontario or maybe North Bay and you get up early in the morning, you're going to see 5 or 10% of the sun occulted. The closest I can get to it for where I live is Barrie, Ontario, with 0.2% occulted. That's ironically where my classmate lives. And uh, where I live in Newmarket, there'll be no eclipse at ever. But if you get out to the eastern part of the province or you're from that part of the province, yeah, Saturday, first thing in the morning, like I mean sunrise, there'll be an eclipse in progress.
That's really cool, but also the idea of getting up to see a, what was it, a 0.2% eclipse?
Would you even notice it? I
I
don't
don't think
know.
so.
Yeah, I don't think you would either.
It'd be cool, but I don't think you'd even notice it, unfortunately.
No,
Um,
I'm holding out for going to. There's a total eclipse, I think, in 2028, and my wife's been looking for an excuse for me to drag her to Australia for a few years. So I think I'm aiming for that one next.
yeah, I'm still pleased with the 2024 eclipse, which I'm now realizing is about a year ago. So I
Yeah,
guess in a couple weeks that'll be our this week in astronomy history is the total
yeah.
solar eclipse of 2024.
I remember
You
driving
said
around, running, looking for clear patches of sky, and quickly setting up my camera and trying to get pictures. It was incredible.
yeah, I got really lucky with that one because I drove out with a couple friends to Kingston, and I think Kingston was like the clearest area that we got in kind of around the GTA. Because we actually did get a great view of the eclipse. I had my camera set up, it was all ready to go. There were a couple kind of wispy clouds around at the time, but the eclipse itself was remarkably clear for that. And then like 10 minutes after totality, we got clouds and it just became overcast. So
For me, I started off in Rochester, New York, and it was totally overcast, couldn't see a thing. And I was looking at cloud maps and so on, and I saw Niagara Falls, near Niagara Falls. It looked like there might be clear skies. Got there, it was slightly overcast. Got my camera set up just before totality. Totality hit and the clouds cleared. And if you get a copy of the AICO calendar. The cover picture is one just as the clouds cleared, and it's a great picture. So,
yeah, a great calendar too. But yeah, so that's I think that's pretty much it for our show tonight. The only kind of mini reminder slash news item that I can talk about is Messier marathon season is approaching. So if you are one of those people that wants to stay up all night and image all 110 objects in the Messier catalog, please keep an eye on your calendar and keep an eye on the weather. The primary weekend this year is going to be in a couple of weeks on March 29th and 30th, which corresponds to the new moon uh, for March. Um, but the window is still going to be open for kind of a couple weeks on either side of that. So you do have about a month or so to be able to do the Messier Marathon, to observe or to image every single one of the 110 objects in the Messier catalog in a single night. We've done a couple of them at the Observatory. One was in 2020, and then we did one last year in 2024. So maybe if the weather works out on the weekend of the 29th or 30th, we'll try and do a third one. Always a lot of fun. But that pretty much brings us to the end of the hour. So everyone, you have been listening to York Universe, the astronomy and astrophysics podcast written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Paul Mackin and myself, Sana Withers. You can always connect with us on Instagram with the handle at YorkU Observatory and on Facebook at Allan I. Carswell Obs. You can also check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in, clear skies, and have a good night.
Have a great night, everyone.